Well, good morning, everybody, and welcome to today's webinar from Smart Vision Europe. This is kind of a special one-off webinar we're running. We haven't, for those of you who haven't attended any of our webinars in the past, we usually have a rolling calendar of webinars where we do about three in a single day. But this is one we haven't done in a while. We've updated it to cover data science rather than just the term predictive analytics, which we've used in the past. And as a result of that, we've got a lot of people booked on it today, and we expect quite a bunch to turn up. Um, if you haven't attended any of our sessions in the past, and I know some of you have, but if you haven't, you should be aware that we do record them, so you'll be able to listen to a recording of it afterwards. And there's a fair amount of slideware in this one. There's some demonstration. I'll definitely be demonstrating some techniques. But we'll email out a link to you afterwards so you can download the materials. If you think it's particularly useful for colleagues who are unable to attend today, and you can get enough of them together, then we may be able to arrange a rerun of it on a private basis. The best thing to do is just send us an email or something like that afterwards. With regard to asking questions, all the lines are muted, so we ask you to use the chat panel. I won't be able to hear you. We do tend to get a lot of questions afterwards, but people just email us afterwards, and we're happy to address those offline afterwards, especially if we run out of time. I'm joined online today by my colleague Rachel. Rachel will be fielding the questions and making sure everybody's logged in correctly. I'm Jarlath Quinn. I work for Smart Vision as a analytics consultant, technical guy. My background is for working for SPSS and SAS and IBM as a data science statistician type consultant type person. And as a result of that, we've been doing that for a long time. We've got quite a lot of experience in this area and a very particular view on data science and where it fits within the wider analytical world. If you don't know who Smart Vision Europe are, we're a premier accredited partner to IBM. We're a gold partner. We're also a partner to a company called Predictive Solutions and to DataRobot. And we specialize in advanced analytics and big data and data science technologies and that type of stuff. But we also work with open source technologies such as R and Python and Spark. We're a relatively small organization. We're made up of a veteran team of 15 of people, about right 12 to 15 people who have a lot of experience working in the software industry, what would be called the tech industry, I guess, in the world of AI, data science, statistics, advanced analytics, etc. I first started working for, I think, SPSS in 1995, and that was after 5 years working as a statistician in universities. So that means we've got quite a lot of deep experience of applying, advanced analytics, a lot of the stuff we're going to be talking about across many different sectors and many different applications across those sectors in both the public sector and the private sector. I know today, for example, we've got a lot of people in the public sector, a lot of people from central local government, people from the NHS, as well as commercial, people from commercial organizations. And just glancing at the organizations, I can guess some of the applications that would be relevant or important for those types of organizations, because of course we've worked in that area before. So assuming that we've got everybody logged in at this point, we're going to start off with talking about data science and how we got there. We're trying to give an overview of that. We're trying to demystify it. We're trying to talk about some practical examples. And to give a lot of advice to organizations who are trying to get their heads around, trying to think about, well, if we were going to start on a data science initiative, how would we run that correctly, and how would we kind of organize it or plan it to get the best out of it? In order to do that, we need to explain how this world comes about. So the point is that there is a history to this. I'm not going to go through the details of this, but when I first started learning statistics at university, and being taught stats, it's important to understand that most of the stats I'm being taught at that stage, way back in the 1980s, are effectively from the 1930s. They predate computing. So these statistical techniques predate computing. It really isn't until the 50s that methods start to arrive that don't rely on statistical distributions. And that's really the birth of what we would call machine learning at that point. So by the time I'm applying it and applying this stuff in the 1990s, I'm usually using a mix of statistical techniques and machine learning techniques. And I point that out not because it's just historically kind of interesting, but because very often you will hear people talking about an AI solution or a data science solution or something like that. And when you actually look under the hood, amazingly, it's using a statistical engine behind it, something which actually literally predates computing. So just because something's is relatively old and classic, it doesn't mean it doesn't have its own degree of sophistication and appropriateness. And certainly statistics is very, very important in the world of AI, in the world of machine learning today. Across my career since the 1990s to today, one of the things that myself and my peers would be very, very aware of is the fact that we have these competing terms and terminology which tends to gain credence and then fade away. So certainly in the early 90s, it was, a lot of emphasis on statistics. There was only about four or five different statistics software companies around. There was SPSS, there was SAS, there was Minitab, there was Stata, there was Statistica. There weren't that many. It was a relatively small number. By the time we got to the second decade of the 21st century, everybody's doing analytics and statistics is just part of that. So it was kind of a rarefied, very specialist area. But one of the first things that people started to become aware of where the sands were shifting, if you like, was the rise of the term data mining. And data mining became a very popular term. You can see here is just searching on Google Trends, the searches for these different terms, that data mining was already trending downwards by 2004. Google Trends doesn't go back from that point. And that's partly one of the reasons why that was the case was that data mining became a pejorative term. It became a very negative term because it became associated with data scraping and with infringements on people's privacy, particularly by large organizations and by governments. So it fell out of favor as a term. But at one point it was very much the new kid on the block, and data mining really referred to very much applied techniques involving machine learning and statistics that tried to uncover patterns in data that you could immediately exploit. We used to say that data mining was a bit like Indiana Jones, where you try to get in there and just find the information that you required and exploit it, whereas statistics was a bit more like traditional archaeology, where you painstakingly uncovered the model of blood pressure to salt intake or whatever it was. Now, against this background, machine learning was always present. Machine learning is really just the sort of as a paradigm, as an approach, it is almost like a twin or a cousin of statistics, but it's almost like they existed in parallel universes. Machine learning simply means using computer techniques, not necessarily distributional assumptions, i.e., statistical distributions, to find patterns that you can exploit. So things, if you've heard of things like neural networks or decision trees or stuff like that, these are associated with machine learning. Machine learning, of course, becomes more and more important as we move through the early part of the noughties. It starts to pick up. And certainly around about the time that SPSS got bought by IBM in about 2008, 2009, you're starting to see the rise of the term big data. And for a while there, any project that you worked on for these companies, even if it was a little survey project or even if it was a relatively modest analytical project, was often labeled a big data project because that was an exciting term. As you're probably aware, that term has somewhat fallen away by now. And now we're in the world of machine learning and data science. So data science is kind of the new kid in the block, and these are subtly different from each other, but in many ways, these are all describing the same sorts of thing. The same sorts of applications could easily be labeled data mining, machine learning, big data, or data science applications at different points in time without really changing what it is that you're doing. Now, of course, against this, there is an elephant in the room, and that is the fact that all of these techniques, all of them, including statistics, tend to fall under the the more general term, or the most general term of AI. And AI, of course, dwarfs everything else. Now, we didn't call this AI in an hour because we know as practitioners that AI actually is a much broader term. It's such a broad term now that seems to encompass everything. It encompasses everything from predicting somebody's credit score through to a self-driving car. It's almost become meaningless. I saw a survey a few years back where they asked people at a tech company at a tech conference what they classed as AI, and they give them a list of applications. One of them was gears on a bicycle, and the most sophisticated one was AlphaGo, which was at the time the AI system that Google came up with that beat humans in the game in the famous game of Go. And that was the single most bleeding edge AI system at that point. And everything was in between that, everything from statistical techniques to neural networks to, facial recognition, everything. It turns out that everybody in that conference at least picked one of those applications as an example of AI. Everybody picked at least one of them, including gears on a bicycle. So it's such a loose term. It's almost meaningless at this point. We are focused in this world here, this world of data mining, machine learning, big data, data science, statistics, because that's a narrower world, and we're not going to call it AI, though you have to be aware, of course, that some people will refer to these applications and these approaches as AI, and that's just their lookout, and we can't really do much about that at this stage. So that gives you some sort of sense of the fact that these terms have gained credence over time. We should not at all be surprised, of course, to find that data science falls out of favor in a few years' time, and it's replaced by another term, which actually ostensibly covers the same sorts of applications. But as with data mining and big data and all these different terms and predictive analytics, which is one of the terms that we've used for many years, data science is a term that was it has some sort of history to it. It was actually first proposed in 1974 as an alternative name for computer science, but it isn't adopted until people come up with the term data scientist. So it's interesting that somebody had to come up with this job title for data science to gain credence. They had to come up with the job title before the discipline, if you like, became popular, and that was in 2008 by Patil and Hammerbacher to describe professionals who combine programming coding skills with statistical knowledge in order to extract insights from data. So that's where it really starts to take off around about 2008. We should bear in mind, of course, that in reality, this is an umbrella term. It's a term that encompasses predictive analytics, statistics, skills in programming and Python, machine learning, people who know about regression, people who know about neural networks, people who know about, writing R code, and people who know about automating that and integrating it into a wider world. This is the traditional stamping ground, if you like, of the data science. It's data scientists. So data science is an umbrella term, very important to understand, encompasses a wide portfolio of skill sets, disciplines, and tools in technology and analytics. So zeroing in on that, let's look at what are these skill sets, what are these disciplines, and what are these tools that data scientists use so that we can start to understand the landscape that they operate within. So first of all, disciplines. Where does data scientists come from? Well, these days, of course, there are data science degrees. There are master's degrees and even undergraduate degrees in data science. But certainly traditionally, these people have come from statistical backgrounds. Sometimes they've been doing computer science or machine learning. They might have been working in an AI application. A lot of people working in physics, things like OR, operational research, econometrics. Certainly from my generation, I'm in my 50s, a lot of people would have come to data science through the statistical realm, and their actual background, a lot of them would have been in social sciences because there's an awful lot of reliance on statistics in social sciences such as psychology and sociology to do surveys and experiments. So people gain their statistical skills there, and then they'd be introduced to machine learning and other techniques. And if they've been around long enough, they would watch the evolution of data mining and big data and AI and data science techniques just naturally as a course of their career progression. So there's lots of different sort of I guess STEM type subjects that people may come from that have data science expertise. In terms of their actual skills, this is harder because, it's almost like a Venn diagram where there's a great deal of overlapping. You rarely going to encounter everybody who's got, 100% skills in all of these areas, but certainly, they would be expected to understand, they would know that they'd be expected to know their stats, they'd be expected to know a lot about different statistical disciplines and approaches, whether it be things like simple regressions through to, survival analysis or more esoteric techniques. They'd be expected to understand how you build and assess models. They'd be expected to know how to visualize data, how to prepare data, how to scale it, and how to clean it. They'd be expected to know how to do a bit of coding to varying degrees. Some people only work against coding. They really work within a coding world, and they use things called notebooks, which they share with one another. They're writing Python, or they're writing R. They're combining both of them. They're expected to know a bit about data management. About how to, particularly if they're having to work in a world where there's a lot of data, where they're having to scale up, they're having to fire procedures, across vast amounts of data, billions of rows of data in seconds. They need to understand something about cloud computing because these days, of course, everything's on the cloud. There's increasingly less stuff that people are running on client or on server PCs. It tends to be out in the cloud, so they need to understand something about that. And they need to be au fait, of course, these days with terms related to AI and what people mean by AI within the realm of data science. And then in tool sets, well, this drives employers mad because employers these days if they're trying to develop a data science team, they often find that data scientists all use different tool sets. It's very hard to get them to agree on one set of tools to work with. So some guys might be working in Python, some guys might be working in Google Cloud or against AWS. They might be using off the shelf, if you like, tools like IBM Modeler, or they might be using tools like ML Ops tools like Data Robot or Data IQ. They might be working with TensorFlow. It's very hard to find, a unique set of tools that everybody uses. And as a result of that, very typically within particularly large organizations, you will find a kind of a patchwork of different tools that hopefully interact with one another. And if you look at the development by large organizations of their data science platforms, these data science platforms, whether it be Databricks, whether it be Data IQ, whether it be IBM or Google or Microsoft, what they're all trying to do is they're trying to be everything to everyone. They're trying to make sure that they've got a Python notebook in there, they've got an R notebook that they can scale to Spark, that they can run their own native code. They're trying to be all things to all people. It's quite difficult for organizations, but at the same time, it's difficult simply because the nature of the role tends to vary somewhat from one person to the next in terms of where their skill set is. So this takes us to the point, which is really what was data science for? Was it actually produce? And typically when I'm doing a project, and I've done many, many different consultancy projects under the auspices of data mining, machine learning, data science, predictive analytics, statistics over the years, what people expect to see when you show the results of that project is they expect to see pretty pictures. They expect to see nice pictures, nice visualizations. They expect to be told a story and say, this is what we discovered, because that is their normal way of assessing or ingesting the results of analytical work, where analytical work produces charts or produces output that tells them something they didn't know. Um, and you might do that in the course of a data science project. You might well find that we've got a chart here showing me which factors, which variables are driving a particular outcome. That outcome might be likelihood to make an insurance, or it might be causes of rent arrears, or it might be uh, people who are reoffending. Might be different factors, demographic factors associated with that. You might have this chart here. I don't know what the bottom is, but this orange line here is showing the percentage of people who click yes. So let's say it was something like spending or something like that. It's just saying that the more they spend, the more likely they are to click yes over time. So you can see that this variable helps to predict that. That might be useful. Then we have charts up here that help me to assess how accurate a model is, how much better it is than random, etc. That's all possible and quite useful. But we have to bear in mind that although data science is sometimes about driving insight, it is sometimes about about us telling a story, about producing some nice charts. What it's really trying to do is it's trying to create new information that didn't exist beforehand. And that is harder to build a story around because it effectively takes the form of a column of numbers. And that is the end game. That is the output of a data science model. That's what you're going to get. And if you're doing a presentation, you're talking about a project, you're going to struggle somewhat if you just flash up a column of numbers and say, there you go, that's the result of our project. That's what we did. And then you just show them how accurate that is, which would be often the most honest way to describe what you've been doing, because often to produce these numbers that this application produces, it takes a lot of work. It takes a lot of effort and a lot of time, but really that's what you're working towards. It's the new data it creates, which is really important. At which point we say, well, okay, well, what does that new data represent? Why is it so important? What does it represent? Well, it represents so many different things that relate to so many different applications. Let's start with likelihoods. I mean, these numbers here could be likelihoods. These could be probability values. That could be 5%. That could be 1%. That could be 18%. That could be 2.5%. This could be a probability value. Probability of recommending a service to a friend, of completing a Netflix TV series once you start it, of renewing a subscription, of clicking on an offer that's been sent to you through an email, of returning an item to a store, of making an insurance claim, of choosing a university, of a machine requiring maintenance before its maintenance date, of needing a biopsy from a patient, of making a complaint, of a component part failing a warranty and being returned to it, of students completing a course, of people returning to hospital within 30 days after being discharged, of tenants falling into arrears, of important employees, the likelihood of leaving employment within the next 2 years, the likelihood of a mobile phone customer defecting to a competitor, of an employee committing fraud, of a passenger showing up for a flight, giving a certain proportion of passengers, of repaying a loan that's been lent to you, some money that's been lent to you, of causing an accident, of preventing infection. Maybe you're trying to assess a chemical or a protein or a peptide, and it's for its antimicrobial capabilities. Of reporting a crime, what is the likelihood that somebody will actually report a crime given the fact that the crime has occurred against them? Of voting for a political party. Now, these are all applications that I've worked on at some point in time, and it's certainly not an exhaustive list. And that's just likelihoods. That's just when you're just trying to predict the probability of something happening. The other things these data could represent is they could represent the actual estimated scores for individual students, the regional sales for a particular company, the time it takes to complete, a house purchase, blood pressure readings, pollution levels. Done some work in the Environment Agency of trying to predict pollution levels. Hits on a website based on social media, of survival times of patients or survival times of component parts, visits to a museum, visits to a zoo, medical costs, fuel consumption, crop yields, harvest yields based upon different meteorological factors and based on different nutrition fertilizer mixes, traffic volumes, casualty patients. How many that says actually causality patients because casualty patients. Monthly expenditures, pupil numbers. There's so many. So these are all numbers. These aren't likelihoods. These are actual values, property prices, passenger volumes, infection rates, the number of tickets that are sold for an event. These are all applications of themselves. These are numbers that are being produced. And sometimes the numbers aren't numbers, they're actual categories. They could be letters, they could be grades like A, B, C, D. So you could have the customer segment. Something could be the cause of a fault. You've detected a fault. What do you think the likelihood of that cause is? So I've done applications like that where you've got mobile phone masts and you've got a cause, a fault code has come up. It'd be great if the engineer knew what parts to take with them before they actually left the depot, only to arrive on site and realize that they haven't got that part and they have to wait 3 hours on site for a van to turn up with the part. If you could predict that beforehand, the cause of the fault, that would be really useful. Predicting medical diagnosis or helping with that, replacement parts for helicopters, treatment risk groups. What are people's preferred movie genres? This is what something that Netflix or a streaming service would do, but it's trying to make recommendations to you. What mobile phone plan is appropriate for a person, what their level of satisfaction is. Product assortments, basket analysis that retailers do, where they're trying to say, if you buy this product, you buy this product, you should probably, offer this other product with it, or maybe come up with some bundled pricing. Suggested drug regimes. A lot of stuff around document categorization. You get a lot of stuff around, that is a predictive analytics or a data science application where you're saying literally trying to classify documents or categorize them. So we've done stuff in terms of level of secrecy of a document, or whether it should be escalated, or whether it should belong to one department or another department. Customer sentiment, so things like, whether or not somebody's positive or negative about a hotel review. Image classifications, things like, what is this image actually showing? We know this already, or you can search in your mobile phone and say, show me all the photos of cats, and it's obviously classifying or categorizing. It's running effectively a data science application in there to categorize images. And even stuff that we've worked on speech emotion classes, where you're saying, okay, somebody's speaking in a certain way, what is their tone of voice? Are they positive? Are they negative? Are they happy or sad? So there we have likelihoods, we have actual values, we have categories and recommendations. These data could represent any of those things. Okay. And these are driven by models, which you come to in a moment. But suffice to say that typical applications that people mention when they're talking about data science, these are classic ones that people say, oh, that's loyalty modeling. We want to try and predict how loyal a customer is going to be, or their likelihood to defect. We want to predict the next best action in a customer journey. We want to predict, some of these searching on a website, and what is the next page you show them, what's the next best thing to do. You want to predict whether or not a patient is likely to be readmitted to hospital within 30 days after being discharged. This is a common thing. Things like for the past 20 years, certainly, a lot of UK companies, believe it or not, have been trying to predict which pipes they should be inspecting to prevent wastewater sewage flooding. So that's effectively a predictive maintenance application where, rather than using a calendar-based regime, rather than just simply sending out people to inspect a pipe because it hasn't been inspected for 6 months, you'd say, actually, no, it has a higher risk this week than it did, last week, and we should proactively inspect it. There's a lot of applications, not just in the world of predictive maintenance, but in human applications where proactively reaching out to somebody is almost a similar application. Video or voice analytics, you have stuff like cluster analysis, segmentation, anomaly detection, just trying to identify when something unusual has happened. And then forecasting, just the world of forecasting in and of itself, time series analysis. This is a whole world of data science in and of itself, and has its own unique set of challenges. So you'll see these types of applications being mentioned as typical sorts of applications that somebody who works in data science should be familiar with. The more experienced they become, the more they will be exposed to these applications, particularly if they're working for a tech company over time. Now, it's important to understand that depending on the circumstances, some of these applications may be driven by absolutely bleeding edge methods, could be, by the latest version of deep learning, whilst others rely on, just quite old-fashioned methods. I mean, for example, traditionally within credit scoring, people have used logistic regression. Well, logistic regression is a very old method. It's a statistical method, And there are reasons why people use that in in the medical world for things like survival analysis, and the reason why people use that in the commercial world for things like credit prediction, because it's a standard method, because it offers a degree of transparency, and because it allows us to compare one organization's performance to another organization, or one team's performance to another team's performance, or one group to another group. So there are reasons why people might use methods which are, in inverted commas, old-fashioned rather than bleeding edge, and where they might even sacrifice maybe a degree of accuracy in return for transparency. So don't assume that just because it's called data science that they're using, really, really high-end machine learning techniques in the background. So that leads us to some terminology. We need to kind of demystify it. We did say we're trying to demystify it. You will hear terms like supervised versus unsupervised learning. Supervised is really the examples I've been talking about mostly here so far, where we're trying to predict an outcome, we're trying to forecast, we're trying to categorize, we're trying to estimate. And it means when there's one thing that we're trying to predict, supervised is called supervised because we train a model. The term is called training the model to try and predict. Let's say we want to try and predict people who are going to be readmitted to hospital within 30 days. That is an application I've worked in for the NHS. And we have some historical data where we have examples of patients that have been readmitted to hospital within 30 days after being discharged following a non-elective admission. Or we have examples of pollution events. Maybe we're doing something for the Environment Agency. We're looking at pollution and we're saying, okay, we've got here's some historical pollution readings that we've taken, and here's meteorological data and location data and geographical data that we can use to try and train a model to estimate accurately the level of pollution in a lock or in an inshore area. So these are all supervised because we have an outcome that we can use historically recorded data to teach it against. And unsupervised learning is basically where we're saying, okay, we want you to go off and discover artifacts in the data. We're not going to teach you, we're not going to train you. We're going to ask you to find groupings within the data. The classic example of unsupervised learning would be cluster analysis or segmentation analysis, where you're saying, okay, here is my customer data, or here is our client data, here's our patient data, here's our tenant data, go off and do an analysis of this and tell us what natural groupings you tend to find within that data set. It might come back and say, I can see 5 different groups within this data set, and here are the sizes of the groups, here is the profile of those groups, this is what makes them different from one another. And indeed, you might even combine supervised with unsupervised. There's very often where I would do a segmentation or cluster analysis and use the cluster groups that it has found in that data set to help me predict something. If I was trying to predict people's likelihood to renew a service or something like that, I might well run a cluster analysis that finds 4 or 5 groups, and I use those 4 or 5 groups to help me predict whether or not somebody is going to renew a service. So you can use one method to support the other. Then in terms of the data we're working with, structured data is kind of your traditional data, the data that we're often taught to analyze in school and university. Structured data simply usually refers to the data we see in spreadsheets and in databases. This is numbers in rows and columns, and it tends to be categories, numbers, and rows and columns. Unstructured data is everything else. Unstructured data is notes, it's emails, it's video, it's audio. That's data too. Of course, it's messy data. It's often harder to work with and requires some very sophisticated methods. One of the things that certainly happened within certainly the last 5 years is that we've got a new way to analyze unstructured data, and that is what we're seeing with ChatGPT and AI. It does an incredible job of unstructured data. You can actually give it a whole bunch of documents and say, okay, I want you to categorize these documents. I want you to summarize them. I want you to look at these responses to a survey, and I want you to categorize whether or not they're positive or negative responses, and what topics they're talking about. This is very powerful, and this is something which is a major leap forward in the analysis of unstructured data, because typically it's been very difficult to deal with using traditional statistical machine learning methods. But AI is one of the first times that this starts to encroach in this area, and it absolutely plays a blinder at working with unstructured data. Loss function is a term that is used. You'll often see we're trying to minimize the loss function. Loss function refers to error. So when I'm building a predictive model, I'm trying to make the model as accurate as possible. Let's say I'm trying to predict people who are likely to make a claim on insurance or something like that. You know, if 5% of people make an insurance claim in a given situation, I want my model to be more than 5% accurate. Otherwise, if it was only 5% accurate, it'd be no better than random. So my loss function would be the level of inaccuracy, which would be 95%. It'd be 95% of the time I'd be wrong if I was just guessing randomly whether or not they'd make an insurance claim. So you want that number to be as small as possible, generally speaking. And this is tricky for organizations and tricky for model builders and data scientists, because usually one of the most important things is to try to figure out how small the loss function is, how small the error should be for the model or for the application to be useful. And really, you ought to do that before you start the process. And we'll talk about that in more detail later. But loss function refers to error. Deep learning is a method you'll hear talking about. I just throw it in there because it's used so often. Deep learning is a type of neural network which really made massive gains in the teens in about 2016, 2017, 2018, right about that time. You really started to hear a lot of talk about deep learning. Deep learning was a very powerful what's called convolutional neural network, which worked best against really large data sets. So when you had really large data sets, this is something which really helped with things like video recognition. I mean, back in the 1980s, somebody actually came up with one of the first applications to recognize images, and that was ANPR. That was actually a system that could recognize and read number plates. Well, the same sort of evolution of that system from an early type of neural network to deep learning meant that you could do things like facial recognition, and you could recognize objects and categorize things in real time. So deep learning is a branch of or it's a type of algorithm or family of algorithms which rely on very large data sets and tend to give much better results than traditional neural networks. ML ops, machine learning operations. You'll hear people talking about, you'll see this mentioned as software and technology and almost like a stage of data science. ML ops refers to basically automating or trying to turn your data science model into an application. So you've built a model, you've used historical data, you've done all the kind of dirty work, and you've cleaned the data and got it in shape. Once you've done that, you say, right, I want to put this into production. I want it to, predict, what categories somebody belongs to every time they visit a website, or to make recommendations to them when they're using an app on a phone. That business of deploying it and automating the process and monitoring the process and making sure that it's working, making sure that it's fair. This is another area, governance and transparency, making sure that it isn't biased or racist or anything like that. And that is part of what's called ML ops, machine learning operations. It's a stage in the data science journey. GitHub is a site which data scientists tend to use, where it's a kind of file sharing site. It's a place where they can write code, very much code focused, pretty much around Python and R and things like that. But it allows them to do very important version control. So version control is where they're writing code and they're updating it and they're fixing bugs and they're going through it and they're adding another version number to it and they're sharing and making recommendations to it. So GitHub is a site, a technology site where people can share, control code versions, and collaborate with one another and even develop code. And large language model is the technology that's behind ChatGPT and other types of models. This is where you expose it to a very large amount of data, what's called a corpus of data, a body of data. It might be billions of records, and from that it creates effectively a set of vectors. So these vectors are basically like fields, a bit like variables in a data set. And ChatGPT relies on a large language model. If you go onto IBM's site, you'll see that they have different large language models for different applications. So there's one, for example, to help you write code. This is a very important breakthrough in data science, the data science world, is that these days, as long as you, generally speaking, if you know the basics of coding, if you know the basics of Python, if you know the basics of R, LLM, large language models, and tools like ChatGPT really, really help you write code so that you can literally tell it. You say, this is what I'm trying to do. I'm trying to read a file. It's a CSV file. It's on this hard drive. I want to read it in. I want to deduplicate it. I want to, I want to remove any duplicate records in there based on the ID field. I want you to calculate the ratio of male to females in it. I want you to calculate the ratio of spending to uh to I don't know, time spent on using a service, and it will write the code for you. So LLMs are really important, not just because they help us categorize things like text and unstructured data, and which we can use as part of a data science application, but also because they actually help us write the code that does that. So LLMs are very much within the AI world. It's one of the bits where large language models are one of the bits where we kind of have an overlap between data science and AI. Okay, we're going to talk about building a data science model, and I'm going to show you an example of that. So let's just talk through how we do that. So first of all, at the heart of data science application is a model. Okay, and we've kind of talked a little bit about this. You can imagine it. We have historical data. And let's say the data refers to people, so their age, their gender, their spending, their region that they live in, their tenure as a customer or as a tenant or as a user of a particular service. And there's some sort of outcome that we're trying to predict or estimate so that we can take an action on it. We're trying to figure out whether or not they cancel their subscription. We're trying to figure out whether or not they default on a payment. We're trying to figure out whether or not they complain, whether or not they are vulnerable in some way, whether or not they will need additional treatment or go into remission, whether or not they fail a test if they're a student. And we're going to use this historical data with this known outcome or result. So we're talking about what a supervised learning application here, that's our example, to create a usable model. And that model is going to encapsulate these patterns that we're going to uncover to help us predict these outcomes. And this is called training. This is the training phase of it. We're developing the model. And once we trained the model and we're happy with it and we've assessed it, something which takes a bit of time as we try to figure out, can we do better? We're going to take new data from new individuals' incidents, and using a model based on the same information, we're going to generate our likelihood scores or estimates or classification. 32% chance of cancellation, 0.13 probability of defaulting. We recommend the genre of true crime drama. We predict that they're going to spend £938 over the next 12 months. These are the values that we're trying to predict. These are the values that the model pushes out. And this is called scoring. So when you apply a model to new data to produce these estimates, these likelihoods, this new data that the data science application creates, this is called scoring. Now, we can then send the model scores, hopefully, to different platforms to help us drive better outcomes. So we could use the model score and send it to an app. Every time they make an app, we say, we recommend you do this. Or the next time they call a call center, we can ask them for their ID and we can look at automatically score them in real time and say, we recommend you do this, or we need to warn you about this, or it's helping us drive content for an email that we're going to send out, or it's helping us surface information on a touch screen that we're using to try to monitor an application, a machine, or some sort that says, okay, we've read the information from this asset. We predict there could be a problem with this. Please check the following components. It could also be a dashboard in a car. It could be a physical piece of mailing, a letter that goes out to someone that's driving a better outcome. So the model scores are sent out as part of the ML ops operation out to these applications, these platforms, contact management, marketing, outbound marketing, workforce management, asset management systems to generate these scores to help drive the better outcomes. Okay, so that's how it works in the sort of technical realm. But in the real world, this is how it works in the real world. The thing is that this business of deploying the model is the single bit where things are most likely to go wrong. It's often the area where people spend the least amount of time thinking about when they start down their data science journey. And really, it's the first thing you should be thinking about. Only I would say only a minority of data science initiatives end up being deployed, and it's usually a planning problem. It's usually something that they haven't thought about beforehand, because a model is not the same as an application. I can build a model and I can predict patient readmission as I have done, but that doesn't mean that the NHS trust that I'm working with can or is willing to do anything about it. I can say Mr. Brown is 3 times as likely to be readmitted to hospital within 30 days as average. If they don't have the capability to prevent that from happening, then they've just got to wait around for Mr. Brown to show up. So predicting something doesn't mean that you've actually come up with a tool that you can deploy in the real world. And that's where data science starts to get uh, not tricky, but it tends to require more help than simply a data scientist. It requires a wider team of people, of interested parties, and it's easily the single greatest point of failure. Until a model is used in the real world to drive real outcomes, it's not an application. It's just a model. And anyone can build a model. As you will see, building a model is a very simple thing to do. Okay, let's have a look at how we do that. So let's jump out. So I've got a copy of this is I'm just going to do this very quickly. This is actually IBM Watson X. This is Watson X. So I can run these procedures here in Watson X. I've only got about 10 minutes here, so I'm just going to do this quite quickly. And this has got some data set here I've got open. I'm just going to run some charts. This is a cloud-based system. So this is using, if you've heard of IBM SPSS Modeler, this is kind of like the cloud-based version of it. And I could do, as you would do as part of this, I could do like some analysis and I could do some little charts here. So I could look at some, the relationship between, let's say, people who churn, this is people who cancel their subscription, and what services they're using. So I can see there's a strong connection here to fiber optic. I can see there's a strong connection here to month paying. That helps me to investigate the data. I could look at, I could say, what's the relationship between spending and tenure and stuff like that and different types. Here's the average month bill. We can see that people on debit bills tend to pay more than people on card payments. There's more variation in card payment. And people on invoice tend to pay less. They tend to have a smaller monthly bill because their usage is less. And I could actually, I could preview the data and have a little look at the data itself. And I could run that and see how well it does that. And it'll give me a little preview of the data. So there's the data set that you're working with. And here's the thing I'm trying to predict. I'm trying to predict this thing at the end here, which is whether or not they remain customers or not. The first few records, none of them churn, none of them defect. They all remain customers. But we've got quite a few thousands of records here. And if I want to build a predictive model, what I would normally do is I'm going to run this while it's doing this, and describe to you what it's doing in the background because it takes a little while to run it. I'm going to run this. This is a model building algorithm. There's loads of different model building algorithms here. Some of these could be statistical, some of these could be machine learning, lots of different technical models here that it's running in the background. If I wanted to do that, what you would normally do as a data scientist is you wouldn't just train the model against all the data. Because if you train the model against all the data, the chances are is you'll do something called overfitting. And if you overfit the data, that means that the model won't work very well when you start to apply it in the real world. It will learn all the idiosyncrasies of the data set that you've exposed it to. It'll be too trained to that data set. So what we do is we tend to partition the data. We tend to split it into 50-50. You can see here's a 50-50 split here, and it's called the training and testing partition. And the training and testing partition means that the model is built on 50% of the data that we show it, but we test it on 50% that it didn't see. So it's like we send them into 2 different rooms, and we say we test it. And we actually asked it here to to rank the results based upon their performance on the testing group. So it turns out that this algorithm method that I'm running here, if I double click on it, I cheated. It actually wasn't one method. It was actually a whole bunch of different methods that we use. So we've actually tons of different methods, and they were all competing with one another. Look, there they all are. There's some of these are decision trees, some of these are regression, some of these are neural networks. All these different methods were competing with one another to create a model. And I asked it to choose the best models. And if I look inside it and say, just view the model that you've created here, it goes off and views that model. And it says, oh, look, the best one was a neural network based upon these different accuracy criteria. Remember, we're trying to minimize a loss function here. We're trying to maximize accuracy. And it says there's another one here. This is a support vector machine. This is XGBoost. Here's a logistic regression. And you could say, actually, you know what? I'm just this one here is a bit. This one here I don't like. That's too hard to work with. I'm just going to use these three. You could use those three and say, okay, and close that. And you could actually ask it to say, okay, show me. If I hit save at this point, you could say, show me what the scores look like on that. And if you run that and it says it shows me what the scores look like, it's just going to preview the data. It's going to show me the predictions it made for that, for the first few records. And what it's doing is it's producing a category. It says, I predict these people not to be churners, and this is the level of confidence I have with that. And then once I've done that, I could deploy this. I could actually apply this to new data. So I've got more than one version of this stream here. So I've got one here called scoring. If I open that up and say, okay, make this current, revert to that, it shows me how I can pick that model up. Let's assume I was happy with it. I picked that model up and I apply it to new data to score that new data and then to deploy it. And I could deploy it and do it directly from this tool here. It would actually take me through a little wizard. Here we go. Look, here's me. New data. I'm using the churn model. I'm actually asking it to filter the data because if I look at the preview here, I'm actually asking it to filter. I'm not filtering the records. I'm filtering out the columns because what I want from the result of this is I'm not interested in any of the data I use to predict the output. I'm only interested in the prediction, the confidence, and the customer ID. And if I wanted to, I could then actually pick this up and I could deploy this model. I could run one of these procedures here to deploy it. And I could then say, okay, outputs and models, deploy this model out for scoring in the real world and set it up to batch. You can see here it says new job. I can say create job. And it's basically going to take me down through this wizard here. So where you define the details, you notify, you can create a little schedule and say, okay, I want you to run this every Monday at midnight, or at 1 o'clock in the morning, and then repeat it every other day to produce the latest scores that we can then take account of. In a nutshell, that's how we're building it. That's how we're doing this scoring process. Now, what are the real world challenges with data science? I'm just finishing up here. One of the first challenges is that there is a prevalence among organizations to think that if you build it, they will come. That if you get all the gear, if you go and invest in it and start hire people, that your data science AI application will just happen. And that absolutely will not happen. That's not, So you get a lot of situations where you have people with all the gear but no idea. And this happens with really large organizations. I mean, there's many times where myself and my colleagues have been to see an organization and asked them about, this new data science initiative they've got. And the answers have been fairly vague. They're kind of shopping around. The reality is that, the CEO or the head of the organization wants to have a data science function or wants to have an AI function. So even big companies make the mistake of thinking that data science is all about having, a new data science team or a cloud-based AI platform or sophisticated storage and process architecture. They go off and invest in this and then hope that something's going to happen as a result of it. Now, it turns out that very often things don't happen, and you can actually see this among the data scientist community. So if you go into like the Reddit data scientists, certainly back in the days, you would see Redditors and data scientists, saying, look, I've been hired as data science, but I'm not doing data science work, or the current data science job is unfulfilling and demotivating because what they don't know what to do with them once they've hired them, and they end up doing basic queries and some rudimentary insight tasks. They're doing some business intelligence work. They're doing a little bit of statistical survey analysis. Some companies may use the term data scientist as a buzzword to attract talent without a clear understanding of what the role entails. And that is a more common situation than you might think. Now, it's important to remember that there is help. There are useful methodologies out there that are dedicated to data science. One of the ones that we tend to use down the years, and one of the most popular ones, is actually got the term data mining. It's called CRISP-DM, Cross-Industry Standard Process for Data Mining. You could call it Cross-Industry Standard Process for Data Science. Could be called CRISP-DS or CRISP-PA for predictive analytics. It works in either situation. And it's important because these methodologies keep everybody on track, and they illustrate that it's not all just about building models. For example, if you're doing an application, you should expect the very first time you work on a project where you're exposed to new data, that new data probably hasn't been collected with analysis in mind. So data scientists may spend 50 to 70% of their time just wrangling and preparing the data to work on a new project. So the CRISP-DM methodology, for example, has its own website, and it has there's a lot of people talk about it, a lot of webinars and a lot of information out there. It's been pretty well established. Okay, this last set of slides here, just important questions for intrepid adventurers. These are the things that if somebody's thinking about, embarking on a data science career, or they're thinking about, planning a data science application, these are the questions one should be asking of yourself, which is, what does good look like? And this is one of the hardest questions. So you'll often say to people, what is it you're trying to do? We're trying to predict whether or not people need to be credited, or money back, or we're trying to predict whether or not people are going to fall into rent arrears, or we're trying to predict whether or not people make an insurance claim. You say that's good. Okay. How accurate does it need to be, for example? What does good look like? And what they'll say invariably is, we don't really know at this stage. We just want it to be as accurate as possible, and then we'll make a judgment. That's a massive red flag there. If they don't know how accurate it has to be beforehand in order for it to be useful, then nothing will happen. It will never get beyond a model. It will always end up a model and never turn into an application. It will not reveal itself to you. You have to plan beforehand. You have to say, look, if it was 4 times as accurate as the current situation, with this level of inaccuracy, with this amount of false positive and this amount of false negative, false alarms and false alerts and false alarms and false opportunities that we've missed an application and missed a problem. This is what we would do. So you need to almost work through a few scenarios and say, well, if the model was this accurate, this is what we'd do if it was that accurate. They need to understand what good looks like before they begin the process, because the process won't tell you what good looks like. Only the business, only the circumstances around which the application is going to run will tell you that. Second thing is, what will you do differently? If you can do this, if you can meet your threshold, if you can predict this outcome accurately, if you can estimate it, if you can forecast it, what are you going to do differently as a result of that? Because that's when you realize it starts to impact on other people in the organization. This is something which is wrapped up in CRISP-DM. CRISP-DM talks about this, about the problem of deployment. What are you going to do differently as a result of? You might want to do like a test in a train. You might want to say, okay, we're going to do everything as business as usual in most cases, but we're going to take a few examples and just test them out, see how this application works. How will you know it's worked? How will you know it's actually made a difference in the real world? You're going to have to record one group against another group and say, okay, well, if we use this application, this model that we developed, we notice that it's this much better. You have to be planning this stuff very early on. Otherwise, you're not going to be able to sell it to the wider business. It's not going to happen afterwards, after you've built the model. It's something that you have to think about beforehand. Does everybody agree or understand? Very often when you have a group of people and stakeholders involved, you will find that everybody's got a different success criterion associated with it. Everyone's got a different understanding of what it is they want to do. So you need to make sure everyone's on the same page. This is, again, why using a methodology is so useful. And then think about what methodology you will use, because we recommend you use at least some methodology, even if you come up with your own methodology. But you can Google these. ChrisDM's a good one, but there are other ones out there. Think of the methodology as a route to successful deployment. You should bear in mind that we actually have a free ebook you can download. It's called The Insider's Guide to Predictive Analytics, but you could call it Insider's Guide to to Data Science, the same sort of application. You can download that for free. And you should be aware that we have a number of services we offer in consultancy, training, and even data science recruitment you can reach out to. You can source your SPSS licenses from us if you already have them. We have a lot of materials on our website, videos, recorded webinars. We offer no strings attached technical business advice to anybody, to all comers, irrespective of whether or not they're customers of ours. And we also we offer Smart Vision Europe customers access to our free training, our training libraries. We have training library there of materials that you can download. Some of them you can play around with yourself. That would include things like how to use Introduction to SPSS Modeler, which would be a really good way to teach yourself something about data science applications. I hope you found that useful, and we look forward to you logging in again in the future at some point. Thanks very much.